Okay, good afternoon everyone. So we are in week 10, second class, and today inshallah we'll try to finish this part of chapter 5. I hope that we don't have difficulties in here. Let's see. Let me try something. Okay, so far so good. Alright, so what we did last time, by the way, can I ask a question here?
Yes.
Did you revise what we did last time? No, not last class, it will be the week before last week. صح ولا لا? It's been a while, huh? What did we talk about when we talk about the amplification? We mentioned very important parameter. What did we call it? No, voltage is 2 days. It's written there. We need something else. Okay, something that is really very important in MOS amplification. Trans-conductance, very good. And that's what we did last time. We have spoken about the trans-conductance, and we said that why we call it trans-conductance, because the MOSFET, when used as an amplifier, in which region it has to be the MOSFET?
Saturation.
Exactly, because the MOSFET in saturation works like a VCCS, voltage controlled current source. Let me check that a little bit. Anyways, it seems that we have whole problems with this. In any case, we'll go back to this. This slide is enough. And we said that we, in the transconductance, why we call this parameter transconductance? Because it relates the output. What is the output in this case for the MOSFET? Is the drain current. The drain current. We mean by that drain current, of course, the current that we generate with the AC signal. So is that variation of that current with respect to the input voltage, and when you divide that output current to the input voltage, we are talking about here AC, we find a parameter that is unit of conductance, yani the inverse of resistance. Remember? The conductivity parameter sigma, if you remember, is equal to what? 1 over rho, resistivity. Very good. So this transconductance Gm is the same unit as sigma, the conductivity, and that's why we call it conductance. Okay. Regarding the word conductivity, why conductance? That's a linguistic issue. We don't have time to play with that. And then we said that it's called the transconductance because the input voltage here is not on the same terminal like the current. We'll see that in the next circuit. Because if you look here, is the variation here of the AC voltage here creates the current in here. So this terminal is different from this. So this conductance is here. But who creates that is the voltage there. So it's like transfer conductance. And that's why we call this a MOSFET. We call it transistor. Because it's creating a resistor not on the terminal where we apply the voltage, no, but at a different terminal. And that's why we call it trans. Because it's transfer, انتقل. فهي ناقلية متعدية أو انتقالية من terminal إلى terminal آخر. Very good. And we have approached this problem in two ways. There's one way using the small signal analysis, and for small signal analysis we said to find the transconductance is basically to develop the equation for ID which is the instantaneous, and then we separate the DC from AC, and then we said to get rid of the nonlinear distortion here, or to make it as small as possible compared to the linear part, what we do, we make an assumption. I'm hearing some noise, so please, let's keep the class quiet. And for that, we said that to neglect this compared to this, we have basically to follow these equations. And we found that the AC signal should be less than 2V overdrive. So this is the only condition that we need to have in order to apply the small signal analysis. This is a very important condition to use this small signal analysis. However, we said also, here is just a revision because it's been a while since we discussed about this. We said, okay, when we follow that approximation and we follow these mathematical, the development or analysis, we found that Gm was equal to, previously, Gm was equal to what? Was equal to Kn V over drive. This is nothing but Kn V over drive. Very simple. This is GM, okay? So this is GM. And we said also that graphically speaking, we can also get GM by deriving ID with respect to VGS, and this is the curve that relates ID with respect to VGS. Of course, the condition for this is that VGS has to be above VT, and that's why it starts at here. And also, the other condition is that VDS has to be in saturation, has to be greater than V
overdrive.
V overdrive. Oh my God. Are you prepared for the second, for the quiz next week?
No.
I know. So wake up, huh? So we have to have VDS above the overdrive in addition to VGS above VT. Very good. So we said that if we then set the VGS at a given value, we call that biasing. We'll talk about biasing next week. We said if we set basically the current at a given value, ID, and at a given VGS, okay, and then we apply an AC signal that you see here in blue. It has to be small, huh? It has to be small. Small how much? Well, it has to be small. That means this variation has to be way less than 2V overdrive. Yeah, remember that? Well, it has to be. You can see that this variation is way less than 2 of these. You see, it has to be like that. And this, where it was, we discuss it here. Okay, we follow it again. I'm pointing you to this, to the condition for small signal analysis, which is this one. This is the AC voltage. It has to be less than, AC voltage means variation, peak to peak, okay? Has to be less than 2V over. That's what I wrote there. So these are quick, quick refreshment of what we did. If we were not in the class, I will charge everyone 10 dirham. Because this is what you should do at home. You understand? It's not part of today's class, okay? All right? So please revise. Revise. It's very important to understand what's going on. Because from now on, I told you, we will move fast. If you don't revise, you miss something, and then boom, boom. You build then a bubble instead of building a wall. You know what's bubble? Fuqa. That means if nice question in the midterm, the bubble will burst and nothing will happen. But if you build a wall on very strong fundamentals, very strong grounds, then will not do anything for the wall. That's what I mean by revising. You have to make your fundamentals strong. Now today's class, what we do, we touch what we call the voltage gain. Now in here is actually the output voltage divided by the input voltage, because we call it voltage gain. Okay? So it's not transconductance. Very good. So to do that, of course, we go back to the circuit, and basically the output voltage will be this voltage. And the input voltage is this one. However, we don't take the whole voltage, because this voltage, is it DC, AC, or what exactly this one? Small, capital?
AC.
AC. Who said DC?
No, AC, DC. لا هذا instant.
Instantaneous. This is AC plus DC. No, it's not AC DC. It's AC plus DC. There's a big difference. So listen. So we are here looking at the instantaneous, the total AC plus DC. Okay, like here too. If you look at that. But the gain that we are talking about is not the whole voltage by the whole voltage. No, it's actually the AC voltage at the output, which is like this. Yes or no? By the AC voltage at the input. Because DC does not interfere. What interferes here is actually the AC. So the DC will set the bias of the transistor, and the AC is the signal that we need to amplify. We don't amplify the DCs. We amplify only the AC. Very good, very good. I know you know Kirchhoff, yes or no? How much is this voltage? VDS, the instantaneous. This voltage, this voltage here. VDD minus
VGS.
Well, RD, ID means this voltage minus the drop of voltage in here. Very, very good, very good. Which is nothing. VDD minus ID, RD, ID, and as you can see, is the total current here, and here is the total voltage. Yani instantaneous. When we say instantaneous, yani total. Very good. Then we have this total current is actually, or instantaneous, is DC plus AC, yes or no? And then we bring the AC parameters here, this times this, and this together, boom. And the AC parameters, which is this times this, separate. Now this is also instantaneous, yani it has a DC and then AC. This is obviously DC. Why? Because all parameters are DC, yes or no?
Yes.
Very good. And the rest will be AC. Boom. Boom. That means the AC signal is VDS is equal to minus RD ID. You see how simple is that? Very good. Woo. So this is the AC voltage at the output. That's what we are looking for. Very good. And ID, we know that ID, which is the AC current, yes or no?
Yes.
It was created by what? By VGS, the AC voltage, yes or no? How? Through GM, yes or no? And if you remember, again, revision. Revision, okay, let me see that. We wrote that somewhere in the, GM is actually current at the output, the AC, divided by the input voltage, AC, yes or no?
Yes.
Very good. So ID is equal to GM VGS, yes or no?
Yes.
Excellent. Very good. Now from here, we replace that in this equation. Where is that? I like origami. Okay, good. So now we replace this by this, and now we have here the input voltage, and here's the output voltage. Thank you very much. We bring this on that side, it become here, yes or no? Huh? Yes or no?
Minus RD.
So this will be what? Will be the gain. That's the voltage gain.
Okay.
Now something really important here we have to mention that you can see. What's the unit of the voltage gain?
No
Unitless.
unit.
Unitless.
Because volt over volt. No,
No unit.
nothing.
Well, because volt over volt is equal to 1. That's okay mathematically speaking. But as electrical engineers, we should mention that is voltage over voltage. Why? Because it shows that this is a gain, a voltage gain. Is a voltage over voltage. Do you understand? Because we have also current gain, ampere over ampere. So how can we distinguish this number from this number? So we have to give them some signs. So the sign for this, so the unit for the voltage gain is always voltage over voltage. Do you understand? Good. So it's equal to 1, but we write it that way to help us. Remember that we are talking here about voltage gain, not about current gain, for example. Or not something else, okay? Do you understand? To make sure that we know what is this for. Units are important, you remember, right? As I say, usually, 5 eggs is not like 5 watermelons. Same thing story here. So, units are important for a reason. The reason here is not to mention that only, to see the value, but also to see where this come from, or what is this exactly? Is it kind of gain? Is it kind of, of numbers, any numbers of watermelon on X? No, it's a voltage gain. So if you miss this, it's part of the number too. Although it doesn't change the value, but it changes the type, the nature of the number, okay? The color, if you want, of the number. So this is the color of the voltage gain. Always use this unit, otherwise you lose marks, and you don't want to do that. Very good. So now we come to explain that graphically. Now, when we look at the voltages, this is the input voltage. Of course, this is the instantaneous. Again, this we asked about it last time in one of the quizzes. We say that we have an AC signal over, on top, or superimposed on a DC voltage. This is what we mean. It means they have an AC that is sitting on this DC. I'll draw it in green here. It's like a wave. It's like in the ocean. There's some waves, but this wave has some depth. That depth we call it DC. Do you understand? This is the DC, the depth. And this is the wave. And this is exactly the wave. AC is called the wave here. Do you understand? So this is the DC value of the input, and this is the AC value on top of it. Come now? Do you understand? Very good. It's like the ocean, exactly. It's like you're taking a cross section of the waves in the ocean. Very good. This is the input. And you can see that this is the DC, and then this is what? This is the AC. I will I will write it the right way, VGS. I will change this a bit later. The condition to apply the small signal analysis, which we are doing right now, is that, don't look at this, this is wrong, is that this VGS, this has to be less than 2V overdrive. This is a condition. Okay? The condition to use those equations. Now, at the output where is it? Is that the VDS, it has also DC voltage, which is the depth of the output voltage. You see here? And on top of it, there's the waves, and these waves are the AC signal. How much is equal to? It's equal to this times what? Is equal to this. Let me try to do that. Oh, actually, it's easy. Let's forget about this until I fix it. So we call it. So we said VDS is equal to AV. Yes or no? VGS. صح ولا لا? Because AV is output voltage divided by input voltage. Yes or no?
Yes.
And AV, we just found this, minus GM. Minus GM RD. Yes or no? Yes or no?
Yes.
Very good. VGS. It means at any point in here, to find it here, we have to multiply it by a negative number. Yes or no? That is equal to GMRD in magnitude. Okay? GMRD times that voltage. And you can see, because this is negative, that means if this value, if you take this as a reference, if you look at this as a reference, means if you take this as 0, only here, looking at here, that means if the AC value is positive, the AC value at the output will be what? Negative. Yes or no? Here. No. Because you have to be very, very precise when you draw. See? It's negative. And if it is negative, like for example here, so you go straight. Boom, it becomes positive. Why? Negative times negative will give me positive. And the value is multiplied by GMRD. You understand? So what do we call these waves? This wave is basically opposite to this. Yes or no? When this is high, this is low, and this is low, this is high. They are out of phase by how much angle?
180.
180. That's right. Because cosine of 180 is equal to? Minus 1. Okay. So they are absolutely out of phase. Okay? Very good. We said everything. Here we have to mention something also very important in amplifiers. Today's course is very important for the remaining part of this course. I mean the 50% remaining. Very important. Those who missed today's class, I hope they will watch the video. And they pray the video doesn't go away. Why? Because of the following. Listen, this is the output voltage. Yes or no?
Yes.
Very good. Let's go back to the circuit. We need to see something really important. Oh, the bird is back. Okay. VDS. What's the maximum value of VDS?
VDD.
Why? How much? Okay, raise your hand. We said that we need to give others. VDS, how much maximum it can be? Why?
If the voltage drop is 0, it will equal to VDD.
If the voltage drop is equal to? Voltage drop between what and what? Here? If the voltage drop across RD is 0, then this will be VDD. That's true. That's absolutely true. That's absolutely true. This is what it is. Because this is equal to this voltage minus the voltage drop. So the voltage drop, what's the minimum voltage drop?
0.
Is 0. Okay? It cannot be negative because the current is going this way. صح ولا لا? You understand? Very good. We can say like Tamadar said, and by the way, I'm impressed. This is a very good answer. Or we can say the following. This VDD, first of all, is the highest voltage in the circuit. So this is number 1. Number 2 is that if this is VDD, how much is the current here? 0. Because the voltage, so the current here, based on Ohm's law, is equal to what? Delta V between these points, yes or no? Divided by RD. So if this VDD, so the voltage drop here is equal to 0, and it means that the current is equal to 0. So there will be no current passing through if this is VDD. So, and we need the current to pass through. We need that in order to do any amplification. That means if the current is equal to 0, First of all, the amplifier will be where?
Reverse.
If the current here, this current will pass by the transistor, yes or no?
Yes, but if we have
So in which zone, if the current is 0, where we are?
cutoff.
We are in cutoff.
Yes.
Cutoff zone, because at cutoff zone, the current is equal to 0. But here the current is equal to 0, not because the transistor is equal to 0. It's because the circuit did not supply any current to the transistor. Do you understand? So the channel can exist, but there is no current to give. Do you understand?
Yes.
Do you understand? So VDS maximum value is VDD. So what's the minimum value? How low VDS can be?
0.
Really?
Or minus VDD.
What's the condition of the MOSFET to be in saturation? Because we have to keep the MOSFET in saturation, yes or no?
Yes.
So, what's the condition?
Condition is for VDS greater than VO.
Very good. And that's what we need to have. صح ولا لا?
Yes.
Because if we have VDS less than overdrive, then the transistor will be where?
Triad.
Then can we use it to amplify any signal?
No.
That's exactly the answer. Do you understand now?
Yes.
So we cannot allow this voltage to go below V overdrive. Because if it goes below V overdrive, we are in triode, and therefore we cannot amplify any AC signal. Do you understand? Good? Yes. See? I told you this is an important thing, because later on, you will appreciate that. Many questions will come like this. Because this is a part of the game. So now what we say then, the maximum value that we just spoke here about VDS, which is VDD, is actually defined headroom, means how much my head can go in. So basically if you are in a car, some cars they have enough room for the head. You can jump inside the car, fine. We call that headroom. Smell the room for the head. Huh? Without that, then you'll be like this and driving. Like the old cars, the British car, remember that? Yeah. Have you seen Mr. Bean? Yes. Very good. The car of Mr. Bean. You see, the car of Mr. Bean, like, especially in the movie where he brush and take these things, and you know, I like Mr. Bean. So that he doesn't have headroom, you know, for his room. So it means that the signal cannot jump up too much. If we make VDD higher, that means we have higher headroom. Now, for the same thing, cars, some cars they have enough what? Leg room. It means you can put your leg and sleep. This is also leg room, means the minimum value of VDS can go down, but it cannot go below V overdrive. Do you understand? That's what we mean. So now my signal can jump between these two. But outside these two, we don't have anything. The amplifier is not working. Do you understand? See how important is this? Very good. Bye. See you next year or next term. Now we come to the small signal equivalent model. Remember in the diode, we talked about small signal model, Yes. I told you that we are going to see it again, yes or no? Yeah. Now we are seeing it now again. When we said small signal for diode. Okay, very good. What did we do with the small signal diode, a small signal model of the diode? We represent the diode as what?
Battery.
No.
AC.
In AC. As a resistor, remember? Yes. Very good. And that resistor of the diode, RD, is equal to what?
VD plus I.
Very good. Is VT over ID. And then, boom, we study the AC signal. Boom. Very good. Same thing in here. Very similar. So, because when we did the small signal analysis, we found GM, remember? Mm-hmm. How much is the GM again? Kn. V overdrive. Very simple. So, here, we replace the resistor in AC analysis by what? We replace the diode by what? By a resistor that it depends on the DC values of the current of the diode. Yes or no? Yeah. Same thing in here. We replace our transistor with a parameter GM that has the DC value. Where the DC value is in the overdrive. Because V overdrive is equal to what? VGS minus VT. This is DC. Do you understand? It's not AC. That's why the DC we say is embedded مخزن في الvalue بتاع GM. That's why in AC we don't put any DC source, because the DC source, as we did with diode, is removed because it's replaced inside the parameter here of our device. Okay? Got it? See, very nice. Engineers are crazy. And then from here we can make the model more accurate by including the, what you call, the output resistance of the MOSFET. R0, remember? So what does it represent, R0? It represents what? It represents the channel length modulation. When VDS controls the channel length. You see? Do you remember that?
Yeah.
So we said that if we include the effect of channel length modulation, again, if you revise, you will know what I'm talking about. So we said if we include that effect of channel length modulation, we have to put R0 between the drain and the source. Otherwise, in the ideal case of the transistor, we don't have to put a resistor here, because the output current here in DC, it doesn't depend on VDS. There's no resistance. You understand? But if VDS, if we include the effect of the channel length modulation, that means VDS in DC controls the current that passes through the drain. And R0 itself is also a DC parameter. R0 how much is equal?
VA over ID.
Very good. That's another parameter that we need to remember. VA over ID. Excellent. See? And this is the DC. VA is a constant. It's given to you. It's in the data sheet. When you buy the MOSFET, you read the VA. You understand? Good? See? Now we have the AC model, a simple AC model for our MOSFET. Very good. And of course, we don't have any current between the gate and the drain of the source. Yes or no? Because of what? Because we have what we call the insulator. Yes or no? Between the gate, drain and source. Remember that?
Yes.
That's why. So it's similar to that large signal model, but it's a bit different because the parameter here, we are dealing with AC voltage, which is VGS in here, which is this voltage. Okay? Very good. And it's always the current at the gate, is always equal to 0. There is no connection. So, any question? And usually R0 is always a high value parameter. It's actually in the range of 10 kilo ohm to 1 mega ohm. Okay? The larger the better, because if it's too large we can basically take it off and throw it away. And in that case we have the ideal model without R0. So this is basically in a nutshell the small signal model, what we call the small signal model, that we are going to use in every single amplifier. We have 3 major amplifiers. We will use this model again, again, and again. So if you are weak in here, you better go home and revise. Because if you miss it, you will miss the coming 2-3 weeks. And you will miss a very good chunk in the final exam. Okay? So revise, So I want you, okay? Go back and try to revise this, because this is very, very important part. More observations. So here, again, we already mentioned the R0 or R0 if you want, how much it is. So now the small signal parameter, now we have 2 parameters. It's not only GM, it's GM and R0. Sometimes we include R0, sometimes we don't. It depends on our approximation, because both of them actually, they depend on the DC bias. The DC bias will take almost 1 week to talk about that and explain very, very well. So the gain, the voltage gain, like we found it just now, is minus GM RD. However, if we include R0 in the model of the MOSFET, then instead of RD, we have to replace it with RD parallel with R0. You will ask me how we find it that. How did we find this? Why we replace this with that? We will explain that when we talk about the common source amplifier, which is exactly this amplifier that we studied, and we'll see why we replace RD with RD parallel with R0. Okay? Do you understand what it means here?
Yes.
Very excellent. All right. All right, let's keep going now. All right, now let's play some games with the transconductance parameter. And what is that game? So it's basically a simple game, very, very nice one. We have the GM, which is the AC current at the output, divided by the AC voltage at the input, and is equal to Kn, V over drive, yes or no? Excellent. And Kn itself is actually equal to mu NCOx times W over R, yes or no? What do we call this one, by the way? This W over R.
Ratio.
Ratio. Aspect ratio. Very good. So it's the aspect ratio. What did we call this? Raise your hand.
Kn
Kn prime. What did we call it? Kn prime. Who knows that? Raise your hand. What did we call this parameter? Raise your hand. Yes?
Process transconductance.
Process. Very good. Transconductance. Yes. Very good. It's excellent. It's called the process. Process. Yes. Transconductance. Yeah. So transconductance. Is it transconductance? Let's see. Wait a second. Let's see. So transconduct. I'm tired. It's a long word. All right. Is it a parameter? We did not finish parameter. I'm tired. I'm going to fall. Now, is this GM? You have transconductance. This, we call it process. First of all, we call it process. Why? Because it's related to the fabrication. When we say process, automatically we think about fabrication. Means how the factory is making this. Yani this semiconductor. Very good. Now, this is about the process, about transconductance, because this parameter is inside the GM, yes or no? See? This is inside Kn, yes or no?
Yes.
That's why it's a parameter wasit inside the transconductance. Do you understand? So it's a parameter inside the transconductance that is related to the process. And because the English language like to make things squeezed, so they call it process transconductance parameter. Or if you want to explain again, it's a parameter, Kn prime. We are talking about Kn prime, which is mu NCOx. It's basically the definition, is it? The name is like this, but the definition is, it is a parameter that is related to the process, fabrication for process, that is inside the transconductance. Do you understand? That's right. That's why we call it process transconductance parameter, because it's a parameter that comes inside the transconductance, as you can see, inside Kn, which is part of GM, which is the transconductance, and it's a parameter related to the factory, the process, how we make this transistor, okay? Because it doesn't depend on circuit voltage or anything, it doesn't depend even on W over R.
Sir,
Yes?
process transconductor.
What was that?
Process transconductor.
Process transconductance.
Yeah, it's for Kn or Kn prime.
Wait a second. Kn prime, we call it process conductance. This is for Kn prime. And go back. It will be. Let me see. Let me convince you, because it's been a while since we talked about that. Let me try that. Let's see here.
Sir, here.
Oh, no, it's a long ago. Wait. Just a second. Boom. Hold on a second.
Sir, before.
Oh, before?
Yeah.
So you saw it, I didn't see it, huh?
Sir, here.
Here? No. What did we define it? Wait. Before. Wait. Yeah, it's before, you're right. When did we talk about it? Almost there. Hold on a second. Almost there.
Slide
Okay.
15, sir.
What slide?
Slide 15.
15? So which slide I am in?
41.
41, man. Where I have to go. Okay. Where is that? Is it this one? I have here something here. Oh, slide 15, huh?
Yes.
Okay, let's see. Because you know then why we go there then. Alright, let's see. Okay, hold on a second. Let me check that. So let me go there. So, oh no. Let's see. This is for PMOS.
دكتور الكائن بتكون مع ال.
Oh, wait a second. I'm almost there. Don't worry. I'm almost there. Okay, let's see. Okay, almost there.
Sir, here.
No. I remember. Wait a second. You see? Kn prime, what do we call it?
Process.
Okay, this is related to a process. So it's called here. Hold on a second. Let's see. Okay, hold on. So this, we call it process transconductance parameter. And when we multiply it by that, we... no, not this here. I think in
Sir,
this one.
here.
Here, yes. Now, when we multiply it by the aspect ratio, what do we call it? Just transconductance parameter. Because it's Kn, صح ولا لا? See? So it's Kn, it's not Kn prime. Kn prime, the difference between Kn and Kn prime is that when we multiply Kn prime, which is the process, by the aspect ratio, which is designer parameter, then we will have just a parameter that is in the transconductance. But it's not something related to process only. Okay? You understand? That's the big difference between the two. Okay? And that's why one, we call it process transconductance parameter, and the other one, we call it what? We call it just the transconductance parameter. Very good. Excellent. It's good to go back sometimes. You know? Let's go here. What's this? So we have to go. And then, what's this? Okay. All right. Very good. That's okay. We take a break here. Okay, great. Very good. Okay, the bird has gone. So now we come back there. Very good, very good, very good. So this is the one. And now, basically, now we appreciate the name of the process transconductance parameter and the transconductance parameter, which is Kn. Very good. So there is nothing new in here. There is nothing new. We are just explaining the different parts of GM. But the purpose is not there. Woo. If we take the equation of the current in saturation, which is half, this is what? Half of what? Half Kn V over drive square, or Kn prime W over L, V over drive square. If we take this equation, and from this equation we take the overdrive and express it. And we take that overdrive and plug it in the equation of GM, the transconductance. We put it there. Then in that case we will have this equation. You can see that we have here, square root will be divided between these parameters. Yes or no? Square root here, square root there, square root there. So this square root here will be cancelled with this one. Yes or no? So we will have here the square root. Yes or no? And this one will go. Yes or no? Follow me, yeah? I don't want to say stories. Okay? Now, we have here also Kn prime. We have Kn prime. This is also square root. Yes or no? We'll go with this one because this is this square root times this square root. So this will go, and then square root will stay here. Yes or no? So we have square root of this times square root of this times square root of this. Yes or no? Which is this result. Correct? Yes or no?
Yeah.
Got it? Very good. So that's a different equation of GM. You will see what I mean in a second, why we need to talk about that. Now, you said that we have to solve problems in class. Yes or no? That's what. Okay, this is a problem. Let's solve some problems. How does a MOSFET compare to BJT in terms of GM? I give you just here an idea that GM for a BJT is about 20 milliamp per volt. Now here we have Kn prime, we have ID. What's GM for this aspect ratio? How much?
Square root. 2
Square
Kn
root.
prime.
Square root of?
2 Kn.
Kn equal 120.
Hold on a second. Square root of what?
2 Kn.
No, why 2 Kn? 2 Kn prime. That's true. Because we took it, yes. And then square root of? W over N. And then square root of?
ID.
Very good, excellent. So, how much is this? It's 1, yes or no?
No.
So what we need to do? Square root of this. Do we have Kn prime? Yes, we have. So we make now 2 times the square root of Kn prime
Also we have ID.
times the ID square root. How much is equal? 0 point? Very good. What's the unit? Very good. Excellent. That's exactly the one. Oops. Let me try that. Boom. That's the one. Yeah. 0.35. As you can see. 0.35 millivolt or milliamp, sorry, by volt. Okay, very good. Now, if we make this one 100 times, you know what means 100 times? That means the width of the transistor is 100 times the length. That means this transistor is super big, yes or no? So if you make it super big, how much is GM now? Times what?
10.
Why?
Because square root of 1.
Exactly. So this times 10 would be 3.5. Bingo. Thank you. Very good. That means you are following us. So it's 3.5. But yet GM of a BGT is equal to 20. See? That means the trans-conductance of a BGT is way, way bigger than that of the MOSFET. This is very important result. Why? That means the BJT is very good at passing high currents because GM is proportional to the current. We'll see that in the next equation. That means the BJT is very good in power electronics. If we have circuits that need too much of currents to pass through, GM, they do amplification excellent compared to that of the MOSFET. And that's why in mobile we don't have too much of currents because it's low power. Battery is small, yeah? So we use the MOSFETs, not BJTs, okay? Because they are very well at low power, at low currents. They are not as good for high currents. They don't pass that. Now we come to discuss further GM. We said GM, as we explained just now, is basically the slope of the curve ID VGS or ID V over drive. Why? Because remember, we said that GM, if you remember, is the derivation or the change of ID current with respect to the input voltage. Yes or no? Yes. But you know also that, VGS, which is continuous, is equal to V over drive, if you want, which is, yes, which is V also instantaneous, minus VT, yes or no? So any variation of VGS is actually equal to variation of the overdrive, okay? So that's why the slope will be the same as if we make the derivation of ID with respect to the V overdrive, because of this equation. And that's why it's the same slope if I draw that curve with respect to overdrive instead of VGS. Now if I take that slope at a particular point where the transistor is made, we find something really, really interesting. And that is GM, we said that is the slope. So this is number 1. Now the slope, so the slope is equal to what? Is equal to GM. Okay? Now I go to GM equation here, and I say the following. I take this, the value of what? Of this Kn prime W over L, which is what? This Kn prime W over L is nothing but Kn, yes or no? So this is Kn, yes or no? I go here and calculate Kn is equal to what? Is equal to 2ID divided by V over drive square, yes or no? All in DC, okay? 2ID divided by overdrive square. So from this equation, I replace Kn prime. Do you understand? Very good. Now we have, this is overdrive, and this is the overdrive square. Boom. Yes or no? Yes. So I can write then Gm as what? As 2ID divided by the overdrive. Or I can write it, it's like ID divided by 2, I put it under the V overdrive, and V overdrive divided by 2. Yes or no? Yes. I write it like this. Very good. Excellent. So I come here and say, okay, Gm is equal to the slope and is equal to ID over V over drive over 2. Yes or no? Excellent. But then the slope here is equal to this distance divided by this distance. Yes or no? Yes or no? True? That's the slope. Huh? Geometry. Yes or no? Excellent. This distance is equal to what? ID. So this distance must be equal to what? Half of the overdrive, because that's GM slope there. So this must be the half overdrive, this distance. You understand? Did you get it or not?
Yes.
See? So by doing the slope, I can determine exactly where the overdrive, because this point is V overdrive divided by 2. So I can graphically, from the graph, know exactly where's the overdrive. If I know GM, give me GM, I give you the overdrive. See? So either the overdrive will help me to find GM, or the opposite. Or GM can help me, in this case, graphically find the overdrive. Yes or no? Got it? Very good. So, you know, this is the engineering. It's basically fun. If you take it fun. Very good. Now we have 3 equations that are related to GM. So the first equation is what? Is Kn, V overdrive. Yes or no? Or Kn prime, W over R. The other equation, square, 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 2Kn prime, W over R, ID. Or we can use the last equation, which is the 2ID divided by overdrive, or ID over half of overdrive. So which equation to choose?
It depends on the problem.
It depends on what we know and with what we don't know. So sometimes we know, for example, the overdrive. Sometimes we don't know the overdrive. We know the current. We'll use this one, yes or no?
Yes.
And we use this one. Sometimes I don't know how the transistor is made, means the dimension of transistor. So I will use the overdrive and the current alone. Yes or no? But for you, for example, let's think about something really interesting. If you look at the overdrive, if we increase the overdrive, GM increase or not?
Yes.
But what about here? Huh?
Decrease.
Does it decrease?
No.
No.
Yes. Yes?
It's over 2. It's half of the overdrive.
But still, but if this increase, حتى لو كان over 2, the should decrease that. GM will decrease, صح ولا لا?
No.
So GM here, it does increase with the overdrive, yes or no? But here it does decrease, yes or no? So it's confusion, صح ولا لا? Yes, yes, the ID.
If we substitute the ID.
Very good. That's very good. That's excellent. That's the answer. See, when you allow others to think, they think wonderfully. Because ID is proportional to the overdrive square. Remember that? صح ولا لا? See, I tricked you. It's like magician, you know? It's a wizard. They hide something and they, wow, amazing. Where did this come from? Well, it comes from here. Because this guy is overdrive square. And this is overdrive, so this with square by pi. So still, it will increase with overdrive. Huh? See? So do not trust only appearances. Try to dig. Very nice try. See? So, it doesn't contradict. Because this is constant. It doesn't change. Huh? So when we increase the overdrive, it's always GM will increase. So again, it's a math game and enjoy. There's a lot of things we can speak and enjoy. I don't have to, we don't have time really. We have to move on. So, the book, who has the book? 1, and where's the 2? Who has the book? 3? What the rest? Enjoying their life in here? What? You didn't bring it. You have to bring it. So, I will post the tutorial session, I think, because here I didn't include the figure. You see? So we have nothing to do in here. And we don't have time to talk about that too much. So we'll skip this problem for now. We'll go to another interesting problem. Simpler and more exciting. We'll do that after this slide. This is almost the last slide. Almost. Okay? But trust me, we'll solve the problem before we leave. So in real life, the amplifier, how we use a MOSFET amplifier. So basically, we have a MOSFET biased through voltage supply and some resistors here and there. Don't worry about this circuit. We will come and study it again. Don't worry. But all these things. worry only about what I'm telling you here. If you use a MOSFET as amplifier, you have to put always an input capacitance, a large input capacitance and a large output capacitance to not disturb the DC voltage in here and there at the input and the output of the MOSFET amplifier. Because if we change the DC, we change the model. If we change the model, we don't know how much the gain. We are crazy. So to keep the DC separated from the voltages at the output and the input, at the DC voltages, we put a capacitor here. They are called shunt capacitor or coupling capacitor. There's some difference in there. We don't have time to talk about that. But then these capacitors are a must in order to use the MOSFET as an amplifier. This is number one. Number two, the capacitors in AC domain, they work as a short circuit. Okay? Meaning that if an AC signal is sent in here, it will pass through the capacitor. Okay? And will go here, get amplified, and then go through the capacitor in here. But if there is any DC voltage in here, it will not pass through the capacitor because capacitors are not transparent to DC voltages. We will spend a long time to explain this, but we don't have that much time. So the DC voltages cannot pass through the capacitors, but the AC voltages, they can pass from the input to the output. So this is how we use. We will show how we basically implement the model inside the circuit and analyze it, don't worry, in the next couple of weeks. Now we finish today's class with the T model of the MOSFET. So what we studied before this model, we call this one the hybrid pi model. Pi model. And why we call it pi? Because actually if we include the R0 or R0 in here, it looks like a pi. This is this if you want. And this leg is this leg. That's why it's like a pi. And this is this basically, okay? They call it that way to make their life easy. So from this model, the engineers, the guys who started this business, they developed this model to change this model through some steps, very simple steps, to make it this model. Looks like this. So in here, the model looks like the letter T. See, like this T, but sleeping T. Was working too much at night. Very good. So this model, how we get this model? The way how to do that is very simple. We take the current source in here, that is equal to GM-VGS, and we duplicate it in here. This is the step number one. Okay, we put here the same source because this current is the same like this one, so it didn't change anything. Okay, and then after that, what we do? We basically create a connection here between the gate and this this point X. Okay, but it doesn't make any current. We have to keep the current here equal to 0. That means we are not doing anything actually. And then from there, we know the voltage here across here, which is VGS, and we know the current that is passing through this branch. So this voltage divided by this current, we find we can replace this by a resistor, and how much that is? That V is that voltage, which is VGS, divided by GM-VGS. So VGS by VGS. So I have to replace here. Okay, hold on a second. IDS is equal to GM-VGS. I have to repeat this in different way. So here, if we take that voltage, so VGS divided by the current, that is GM-VGS, will give me that resistor in between X and S, then, which is going to be equal to 1 over GM. So in this case, I can take this out and replace it by a resistor that is equal to 1 over GM, and the voltage across that resistor is VGS. And still, the current coming from the gate is equal to 0. So this is just a model. Why we need this model? Sometimes, sometimes there is a need to use this model because it's simple for some amplifiers to use this. And to make it complete, to include R0, we just put a resistor between the drain and the source, that is R0, the responsible resistance for channel length modulation. Okay? Alright, just a model. We will see that model again and again. This is just a summary of the small signal model. These are the 3 equations for GM, and these are the pi, hybrid pi, and the T model of the MOSFET. Sometimes we use this, sometimes we use that. It depends. That's it. Now we will finish today's class with this simple circuit. And here what I want to teach you, again, we did that before, the methodology, طريقة, the way how to solve this kind of problems. So let's see. What does it say? So the question is to design. I'm not scared about designing anything. Design the circuit of this figure to establish a drain voltage of 0.1 volt. Yes or no? This is the one. What is the effective resistance between the drain and the source? What is that resistance? Between the drain and the source. What is that? Between the drain and the source. He means RD, okay? Because he means the voltage source actually. He doesn't mean the source terminal. It's not this one. He means by this the voltage supply source, okay? Okay, so the question is, find RD to make VD here is equal to 0.1 volt. And he asked he told us that the VT, the threshold voltage, is equal to 1 volt, and Kn prime is equal to 1 milliamp per volt square. So how to find RD? Very good, very good. So the question is to find ID. So how to find ID? Very good. See, we are going step by step. So we have to know which region, because each region has its own equation. صح ولا لا? صح. So which region is this one? How to check? What to check to know the region of operation?
VGS.
Wait a second. Let's give somebody a chance. You tell me one condition. There are two conditions.
First, I have to see VDS if it's greater than overdrive or less than overdrive.
Very good. This is one condition. The other condition? VGS? Very good. So actually that's the first one. We have to make sure that VGS is above VT. Yes or no? And then VDS if it is above the overdrive or less than the overdrive. Okay, let's see. Now VGS is equal to what? How much is VGS in this circuit? You raise your hand. VGS is equal to what?
VG minus VS.
I said raise your hand. How much is VGS? VGS is equal to what? This is a simple equation. Yes? Yes?
5.
VGS is equal to 5. Why?
Between the gate and the source.
Very good. But it doesn't matter. So basically how we find the equation is VG minus VS. Do you understand?
Yes.
Minus VS. VG is equal to what?
5.
We look at the G. It's connected to this. It's equal to 5. Very good. So it's 5 minus VS. Where's VS?
Connected to the,
At the source.
ground.
You see, the source is connected where?
Ground.
Very good. Ground is always 0. So VGS is equal to what?
5.
5. VT is equal to what? So do we have a channel? So the first condition we have it. So we don't have cutoff. Yes or no?
Yes.
Alhamdulillah. So now we have to check what?
V over the
V. VDS. How much? How much is VDS? Raise your hand. Raise your hand. Raise your hand. So VDS is equal to what? Okay, wait. Wait. VDS is equal to what? Wait. Wait. Yes. Yeah. VD. Yeah. Raise your hand. Don't worry. VD minus VSE. Yeah. Don't hesitate. VD is equal to what? Continue. VD is equal to what?
0.1.
Yeah. Continue.
0.1.
Yeah. How is that? 0.1. Let her speak. Yes. VS is equal to?
0 because it's connected.
It's connected to ground. Very good. So VDS is equal to 0.1 volt. صح ولا لا? Excellent. صح. So now continue. Yeah. Continue. Yes. So VDS is a 0.1. So what do we do next? What do we check? Wait up. Give her a chance. Yes. Continue. So when we find VDS, though, and then what's next? To know which region. So we have to check VDS if it is above V overdrive or less than V overdrive. Yes or no? We just spoke about that. Because VDS, if it is above V overdrive, we are in saturation. And we have the equation for that. And if it is less than overdrive, we are in triode and we have different equations. صح ولا لا? Very good. صح. So how much is the overdrive? Raise your hand. Yes? Very good. VGS is equal to what?
5.
Is equal to 5. VT is equal to 1. Very good. So V overdrive is equal to? Very good. So we are in triode or saturation?
Saturation.
Why?
VDS is greater than.
V what?
VDS is greater than V overdrive.
Are you sure? VDS is equal to what? VDS, hold on a second. VDS we found is equal to 0.1. صح ولا لا? The overdrive is equal to 4. Which one is bigger? V. So means we are which region we are?
The saturation.
Triode. We call it triode. Okay, not saturation. That means triode. You understand? See how we do it? So we need to know where the MOSFET is working. This is number 1. Do you understand? When we know, and we need to know that, we have to know how to calculate these voltages. I told you this. This is not joke. This is serious. These are the basic of electrical engineering. صح ولا لا? VDS, VGS. So please do not tell me how to find this VDS for you and VGS for you. You look at the circuit, you know what means VDS and what's VGS. Boom. Okay? We get that, boom. Then we know now, so now officially we are in triode. And the equation for that is ID is equal to half Kn V overdrive minus half of VDS times VDS. See? Or we can use something else. V overdrive is 0.1, yes or no? And overdrive is equal to what? 4 volt. So basically we are very at very small voltages of VDS, yes or no?
Yeah.
So we can ignore this compared to this. And we get the initial equation, if you remember, which is Kn V overdrive, V overdrive, VDS, if you remember, couple of weeks ago. Boom. And we don't have half here, by the way. Yes or no? All right? Boom. So I have this equation. We have everything now. Ding, ding, ding. And then we get ID. Once we get ID,
We can find.
very good, which is delta V, which is this one, divided by ID, we get RD. Thank you very much. See you next week. Sounds good, huh? So remember these steps because they are important, okay? Very good. What's that?